Hello. Today we are going to talk about how you can train a neural network or try to understand a multi-layered neural network uh, using a very cool demo that was developed by TensorFlow. It doesn't require any programming. It's just a visual tool to help you understand neural networks. So I would like to thank them first of all because I'm using their tool, and I welcome you to play with it yourself as well. The link for this is posted in the description of this video as well as the lecture notes. So let's see what we are trying to do over here. You're given a classification problem in which you have two classes. There's a blue class and then there's an orange class, right? And we want to find a function that separates these two classes. And what we are going to do is we are going to try to do it using a single neuron first of all. Okay? Let's say we've got two features. There's the feature on the x-axis and then there's a feature on the y-axis. Those are the two features that we have as input. And then what we are going to do is we are going to see if we can change the weights, these weights. You can see the current value of the weight is minus 0.37 and this value is 0.5, and the resulting discriminant that you see is shown by this white line over here. And as you can see, it's not doing a very good job over right now. So if we train that single neural network, we've done it in PyTorch ourselves, but this is a more visual analysis of that. We can choose a linear activation, okay? And as you can see, it has an impact on the boundary that we have generated. For this particular classification problem, the initial value of the weights, we're lucky that we got an initial value of the weights that already solved the problem. So we don't particularly need to do any training. But if we go ahead and do that anyways, this is the line that we get. And you can see the loss value on the y-axis for this example as we go through different training epochs. Okay, so that's pretty simple. And if you look at the final values, those weights are 0.96 and 0.84. So for a very simple data set like this one, a single perceptron is able to separate this or give 100% training accuracy on this. We can change it to a more complex optimization problem or to a more complex data set. Let's try that. Let's say we've got a data set like this one. Now we can see that this is not linearly separable. It's impossible to draw a single line that would separate it out. And if we try to solve it using a single neuron, we can simply play it, and you see that it's not able to generate very good prediction score, and the loss does not go to 0. It just stays at 0.4. This plot over here is what is called a convergence plot, and these allow us to analyze how is the loss value decreasing across different training epochs. So this is what's going on over here. As you can see, there's no learning taking place. Convergence doesn't take place, so we can say that learning doesn't take place as well. Next, what we are going to do is how we can solve this problem. We can solve it by multiple ways. First of all, if we restrict ourselves to using a single neuron, then what we can do is we can add additional features. Okay, let's say we add the square of the first input as an additional feature. So we have a feature that we know over here on the x-axis. What I do is we just add a square of that as another additional feature. Then I can also add the square of the y-axis as an additional feature. Because now we are doing squares over here, our neuron is, or a discriminant is still linear, but we are changing the feature representation. That's the sort of thing that we did when we were talking about transformations in support vector machines, right? So we're doing this, and we can see that all of these additional features that I've added are only dependent on features of that given example and not the labels. So this is a completely kosher transformation. We can see, let's see if we are able to optimize or solve this problem using these additional features that we have added. Oh, and it works, right? And of course it should, right? Because we've added the squares of these to the linear discriminant as well. So we have now more expressive power, more representation power. We've changed the representation of the machine learning model and we've made it non-linear, right? And that is able to solve this optimization problem. The final weights for this is minus 0.39, this weight is minus 0.43, this weight is almost 0, and this weight is almost 0 as well. Because this is essentially a circle, so x1 square plus x2 square is equal to r square is the equation of the circle, hence you get a perfect loss over here. Okay, you can also try with other by adding other features. But in a neural network, or what we can do is let's try with a single. I'm gonna remove these additional inputs that we have added so that we are operating only in the original features, and then let's see if what happens when I change the activation function. Okay, so let me change the activation function from linear to rectified linear in this case. Now it's still, we have a single neuron, but now that neuron is a bit non-linear. It produces a value of 0 whenever its net input is less than 0, and produces a value equal to the net input if the net input is greater than 0. That's the definition of the rectified linear input, right? So rectified linear activation function. Let's see if this works. And as you can see, it doesn't work still, right? We are not able to get this problem solved with a single neuron at the output, because there are no neurons in the hidden layers. Now, if you think about it, just like we added these additional features, we got some extra representation power. The impact of adding hidden layers or neurons in the hidden layers is like they transform the input that is given to them. Those are the raw features that we are giving them as input. They transform them. So you can think of, if you have a single example X, you're adding a hidden layer is going to transform those features into another set of features, which are then given to this final layer neural network neuron at the output, right? So perhaps that would give us enough representation power to then be able to solve this problem. So let's do that. Let's see if I can. So I've added 2 neurons. Let's say if we can get away with adding only 1 neuron. And let's see if I can use, I'm using a rectified linear activation function in the input. Let's change it to linear. Okay. So this is these are the input layer neurons. There is a single neuron in the hidden layer. If you follow it with the lectures, then in this case your n is equal to 2 because you have 2 features at the input. Your p is equal to 1 because there is a single hidden layer with a single neuron, and then your m is equal to 1 because you have a single neuron in the output layer, okay, as well. We want that neuron to produce a value greater than greater than 1 when you have a positive class example and 0 otherwise, right? So let's try if we can solve this. But I want you to pause the video and think first. Would this be able to solve the problem or not? Is this neural network a linear model or a non-linear model? Let's hit play now. And as you can see, it still doesn't solve the problem because your neural network is still linear. There is no non-linearity in it, and this is a non-linearly separable problem. So we need certain non-linearities in it. Let's add a non-linearity. Let me reset this, and let's add an activation function. Let's say let's do rectified linear, and let's see if we can solve that problem. And as you can see, we're still not able to solve that problem because we don't have enough of a representation power right now. We can change it to another activation function, and perhaps this would be able to solve this problem. But as you can see, we still don't have enough representation power. So think of it like this. You have these 2 features as input. Those are getting mapped to a single feature, which is then going into the output neuron. It still doesn't have that. We don't have an effective transformation that would allow us to solve this problem. So what we do next is we increase the number of neurons in the hidden layer to 2. Okay. So we have 2 neurons in the input, 2 neurons in the hidden layer, and then those neurons feed into an output layer neuron. Okay. We have a tan hyperbolic activation, which is just another type of activation. We're going to discuss these activations in a bit more detail in the coming lectures, but you can change it to other ones if you want. Okay. So let's see if we can solve this problem using this. We're trying to adjust these weights. As you can see, these weights are changing as we go through these epochs, but we are not still able to solve this problem. Like, it's a better solution than we had earlier. The training error is for these examples over here. So all of these examples are being classified correctly. These examples over here are also being classified correctly, but it still doesn't have enough representation power. We need to add, let's add 1 more neuron in this hidden layer. Okay. So we have 2 input features. They get mapped or transformed to these three additional features, which then go into the neuron or a single neuron at the output. So if you want to break it down, we have a single neuron at the output, but we have three different, we have a transformation that goes from 2 to 3, and then those three get mapped to 1 in this architecture. Okay, let's reset this first, and then let's start training. So during the training process, what happens is that we calculate the error, that we know the labels of all of those examples in this training data set. Those that is being compared with the output of the neuron, of this output neuron that is being generated, and then we update these weights, all of these weights and biases that you see over here, based on that error signal, okay, using some algorithm. We're going to talk about that algorithm later, but let's hit play for now. And let's see if this, oh, yep, that's a beautiful solution, right? So adding these three neurons with a tan hyperbolic activation is now able to solve this problem. And by solve, I mean we now have a method that we have a classified boundary that is non-linear, and it's able to solve this problem, right? And you can check the values of weights over here. You can check the values of different types of weights over here. In response to our lectures, these weights over here are weights W's, and these are weights V. And as you can see, changing these weights changes the outputs. And all that happens when I hit play is that an optimization method comes into play that tunes these weights in such a way that your error is reduced. And that's what we can see in terms of reduction in the training loss, and this is called a convergence plot. I welcome you to play with this, try to understand the role of different type of layers, different type of activation functions. You can try very simply by changing the activation function from tan hyperbolic to, let's say, rectified linear, and hit play again and see if that is able to solve this problem. As you can see, it still doesn't solve this problem. You can add more neurons in this layer and see and try again. And as you can see, you get multiple cuts, just like we talked about in the lecture, and you get these different discriminants, right? And this is the surface by combining all of them. So it's able to solve these problems. But there is a difference in terms of activation functions. Each activation function has a different impact. Let's say if we choose rectified linear in the activation function, then this neuron, that activation function is applied to all of these neurons, and the behavior of these neurons changes. Okay, so that's the overall impact of all of this. You can try with other activation functions. There are some parameters that we haven't talked about, like the learning rate. It's the alpha value that we talked about in the optimization. When we were discussing optimization of multi-layer perceptrons, we're going to talk about that in a bit more detail. There is also some regularization rate and regularization that we haven't touched. You can also try it out for different data sizes. You can have different type of examples. You can have, this is called a checkerboard pattern. And these two classes are one, and then these two set of examples are in the other class. You can try with that. And I welcome you to play with this. Try to get an intuitive feel for what's going on, what happens when I increase the number of layers. Thinking about it at an abstract level, what happens when you add a layer is a feature transformation. You got an input example that is a point in a given feature space. When I add a layer, so with reference to the output neuron, that representation of that particular example gets changed. And this happens in a way that is also learnable. So we can learn the transformation rather than me specifying or me giving you the transformation. This process happens automatically. We have these neurons over here that learn what transformation or what sort of feature change do I need to make in order to produce my target value. Okay. So thank you. I hope you have fun with this.